Hello, today we will be talking about computing the eigenvectors and eigenvalues of a linear transformation. Recall that eigenvectors are vectors u that are only stretched by the linear transformation. Stretching a vector is simply multiplying its coordinates by a scalar. Here, the scalar lambda is called the eigenvalue corresponding to that eigenvector. So how do we actually find these eigenvalues and eigenvectors? So we can actually use the definition. A times u equals lambda times an identity times u. And then when you reorganize these terms, you can get lambda times the identity minus a, all multiplied by u, give you 0. This means that the columns of lambda times identity minus a are not linearly independent, which also means that this matrix has determinant 0. Now, taking lambda to be unknown, we can form a so-called characteristic polynomial. P of lambda equals the determinant of lambda times I minus a. And now when you set this equal to 0 and solve for the roots of this polynomial, you get the eigenvalues back. Now, how do you find eigenvectors corresponding to these eigenvalues? Once you have the eigenvalues, you can substitute the eigenvalues in, and you can solve for this equation component-wise. And we'll see an example of that in a second. But first off, what is a determinant? A determinant is the volume scaling factor of the matrix when it's viewed as a linear transformation. Negative determinants can signal changes in orientation. The determinant of a 2x2 matrix is fairly easy to compute. For this matrix, with the entries A, B, C, and D, the determinant is just AD minus BC. This is also the area of the parallelogram formed by the vectors AB and CD. Higher dimensional determinants are somewhat harder to compute. Here's a 3x3 determinant, and it is computed recursively using determinants of 2x2 submatrices. So you have each entry in the first row, A, B, and C, scaling the determinant of a submatrix formed by rows and columns that this entry is not in. So A times this right submatrix, lower right submatrix, B times the submatrix formed by these 4 entries, and C times the lower left submatrix. This kind of recursive approach also works in higher dimensions. Now let's see how to actually use the characteristic polynomial with the determinant computation to find eigenvalues and then eigenvectors. So we have the matrix A here with rows 3, 2, and 0, 2. You can form the matrix lambda times I minus A as follows. Lambda on the diagonal minus these entries, lambda minus 3, lambda minus 2, and the off-diagonal entries are just negated, 0 and minus 2. So now when we take the determinant of this, it would be this entry times this entry minus these 2 entries multiplied, but that gives 0. So what you get is lambda minus 3 times lambda minus 2 equals 0, and you see that the eigenvalues are 3 and 2. So once you have these eigenvalues, you can substitute them in one at a time. So if you substitute 3 for lambda, then you get this matrix with 0, minus 2, and 0, 1 as the 2 rows. So you want to find the vector with subcomponents x, y such that if you multiply this matrix by x, y, you get 0, 0. So in particular, that means that y has to be 0 because minus 2 times y has to be 0. But x actually can be anything. So to pick a vector with unit norm, we picked 1, 0. Similarly, we can find the other eigenvector corresponding to eigenvalue 2. So now you substitute 2 for lambda, and you're getting 2 minus 3 and 2 minus 2 along the diagonal. So you got minus 1 and 0 along the diagonal. And the off diagonal is 0 minus 2 still. Now you see that negative x minus 2y equals 0, or negative x equals minus 2y. So this, for example, could be 2 and minus 1, or any scalar factor of that. Now, this method can get pretty computationally complex to compute in higher dimensions, there have been other methods that are used in the past. One such method is the power iteration method. In this method, to find the largest eigenvector of a matrix A, you start with a random vector, and you repeat this until convergence. This involves multiplying this random vector by A and rescaling it to have unit norm, and then using this as the next iteration vector. So this will eventually converge to the largest eigenvector or the eigenvector corresponding to the largest eigenvalue. So why does this work? If A has a dominant eigenvector u, then the random vector will have a component in the direction of u. And when you apply A to this vector, it stretches the component that's in the direction of u, and so it becomes a larger part of the next vector, and so on and so forth, until it entirely consists of u. So now, in the power iteration method, we first found the eigenvector. Now, how do we find the eigenvalue? For that, we use what's called the Rayleigh quotient. The Rayleigh quotient is this expression right here. This is a quadratic form, u transpose times A times u, divided by u transpose times u. If you substitute in lambda u for AU, you see that this lambda term can come out, and these two factors cancel, and this gives you lambda. Here's an example of the power iteration method that I coded up and applied to this matrix. And you see it converges in 1, 2, 3, 4, 5, 6 iterations. This is to find the largest eigenvector corresponding to the eigenvalue 3. The next eigenvector can be found using this method, but you first have to take out the largest eigenvector. So to take it out, we form the outer product of u times u transpose, scale by lambda, which here was 3, and then you subtract that from A. So now B is this new matrix whose largest eigenvalue is the second largest eigenvalue of A. So we took the eigenvector corresponding to eigenvalue 3 out, and now we have this new matrix, and we see its eigenvector immediately within 1 to 2 iterations. Remember, I talked last time about eigendecomposition, which is actually decomposing a matrix into products of eigenvectors and eigenvalues. The eigenvalues were all along the diagonal. The eigenvectors are in columns here. But I want to make note that not all matrices can be eigendecomposed this way. Matrices that have multiplicities in their eigenvalue, but not equivalent multiplicity in their eigenvector, cannot be eigendecomposed. An example is A, which is 1, 1, 0, 1. Here we see that the eigenvalue 1 has multiplicity 2, but there's only one corresponding eigenvector. So this is an example of a matrix that cannot be eigendecomposed.